So this is our physics project. My name is Robert.
I'm Brendan.
I'm Jack.
And always remember, more physics, more fun.
So for our physics goal, we want to test the centrifugal acceleration necessary to flip 180 degrees in a hammock through the dynamics lens. And we want to test what is easier, flipping in a traditional way or getting in upside down and then flipping. Think about this.
I thought about it.
This is my Eno hammock. It's hung right now between tree A and tree B. The distance between tree A and tree B is 10 feet. Each strap is strapped 6 feet tall from the ground up on both trees. And the distance from the ground to my ass is 2 feet and a quarter.
Hey.
We use Logger Pro here, and I set the point as to where I was starting, and I was able to figure out exactly where I was moving in the video at this time frame right here at 1.928 seconds, and my final time frame when I finished the semicircle at 2.162. And when I go here to this graph, it shows me this is my perfect semicircle right here.
So when we look through a dynamics lens, we know that there's a total change in time necessary to facilitate this rotation. And we know using our video in Logger Pro that our final time was 2.15 seconds, and our initial frame rate was 1.928 seconds. Taking the change in that, we know our change in time was about 0.2 seconds.
Okay, so in order to calculate my angular velocity, I had to input my change in time in the video and my change in theta. And so my change in theta is going to be 1 pi because I'm moving a semicircle, which is only going to be 1 pi. And my change in time given here is 0.22 seconds. And when you divide that out, the answer is going to be 4.55 over seconds.
Knowing our angular velocity, we can calculate our linear velocity. We know that our angular velocity times the radius of our half circle will give us not only our answer, but the correct units, meters per second. And so when you multiply that out, we got about 3.4 meters per second. Finally, we can use that same linear velocity value and plug that in for centrifugal acceleration. We know that velocity squared over the radius will give us some centrifugal acceleration. Therefore, 3.41 divided by the 3/4 of a meter gives us about 15.5 meters per second squared. And we know this works because the units cancel out. We know that meters squared over seconds squared divided by meters gives us the meter per second squared we're looking for. So we have pretty much everything now. We know the change in time, we know linear velocity, and we know centrifugal acceleration. But exactly how much force was used to do this? We know that the change in force of a system is the mass times the acceleration, centrifugal acceleration. We know that our hammock plus student was about 78 kilograms, and we know our centrifugal acceleration was about 15.5 meters per second squared. Putting that all together, you get kilograms meter over second squared, or newtons, and we got a little over 1,200 newtons.